So as most of us know, like these days, if you see all the systems, I mean, they have been put together in a commodity manner. We have multi-core processor and especially high performance network, the accelerators both from the NVIDIA GPU side as well as the MIC. And then of course a lot of the new things are coming, the SSDs, NVMe SSDs, NVRAM, etc. And at the same time also we have the parallel programming model where MPI has been the common, but also this PGAS model is coming. Also people are talking about hybrid MPI and PGAS. So in that context, if you take a look at where MVAPICH most of the work takes place, so that is kind of the programming models we want to support, and these are all the different components which are coming, the commodity component, the networking technologies, multi-core architectures, the accelerators, and of course we need to deliver the performance to the application layer as Thomas indicated, the end application, if you can deliver the performance and scalability, that matters. And typically these are written on top some middleware, and now the question is how do we really bridge the gap here, and this is what we have been working, the communication library or the runtime. You take either MPI or MPI or PGAS or MPI PGAS. These are the kind of different components we put it together to make sure that we are taking the best advantage of these technologies and delivering the performance and scalability. So this is a layered approach, but a lot of people also work in a co-design approach, and we have also done several kind of things within the MVAPICH2 project also, working across multiple layers and then trying to deliver the best performance and scalability. So in general, as you know, the people in the community have been talking about MPI plus X. X could be as simple as OpenMP, or it could be as complex as any other PGAS. And these are the kind of a list you come up with, saying these are the wish list any runtime or communication library needs to do, starting from scalability for point-to-point communications to collective communications to balance intra-node and inter-node communication, because these days the number of cores per node are increasing. Then you need to provide some good support for multi-threading, integrated support for GPUs, accelerators, fault tolerance, QoS, hybrid MPI and PGAS programming. Also there is a lot of focus these days on HPC cloud, there is a virtualization, also energy awareness. So these are all the kind of topics, and we in my group actually have been taking a very holistic perspective of all these angles. So when we try to come up with the MVAPICH2 stack, it actually touches a lot of these points. So we started this project, as some of you know, almost like in the year 2000 when InfiniBand came into picture. Prior to that, we were working on Myrinet, Quadrix, wormhole routing, SP. So those were all old systems. So I'm very happy to say that like now this year we are celebrating 15 years of this project. We started almost like 2001. Thank you. So 2001, the initial papers came out. The code actually came out. The first time it was available in the supercomputing 2002. And then since then, we have been like, originally it was MVAPICH1, then gradually we moved to MVAPICH2. Then after that we have been, because the field is moving so fast, we have different kinds of versions to satisfy different segments. MVAPICH2 is the main one, but then there are these different derivatives. I'll talk a little bit about those. And now so far like it's being used by more than 2,600 organizations in 81 countries, and these are based on voluntary registration. So when people download, we ask them whether to identify. Actually there are, I think another factor of 2 or 3, they just download, don't identify, that's fine. But these are the registered organizations, and we crossed almost like here you can see like a 380,000 downloads. So we are hitting by, I think by this end of this year we'll be crossing 0.4 million downloads just from our site. And of course people use it in all different stacks. They are available in all the different Red Hats, SUSE, all kinds of disks. But not only it's just the count, I mean we have been empowering a lot of these clusters over the years. Here I just give some data, like some of you might be knowing there was a System X from Virginia Tech. That was like the number 3 system in 2003. That was the first InfiniBand system. Many of you might not be knowing. It was only like, you see, 2,000 processors, only like a 12.25 teraflops. So we have been working in the community since that time to like the latest one is the TAC, which is like almost 500,000 cores. And on all these systems, these are like production It is running on a production manner, and just like Thomas said, on the CSCS system, this is the real production weather forecasting is taking place. So, so MVAPICH2 is driving those kind of environments. So this was a very quick timeline. Like we started with MVAPICH. Then you might be knowing we have a OSU micro benchmark. So every time we introduce some new features, we also put the corresponding benchmarks so that people can play with it, people can experience how to write programs, people can also evaluate the performance. And then we started the MVAPICH2, and then we declared the end of life for MVAPICH, and after that we had the MVAPICH2-X, which supports all the PGAS models, also the hybrid API PGAS model. Then as the GPUs became very common, we started this optimized version for MVAPICH2 with the GPU direct RDMA. And then similar things also we have done for the Intel MIC, and then we are moving into that direction towards KNL, Omnipath kind of thing. And then with the HPC cloud, we have the MVAPICH2 virtualization. And last year we also started an energy aware version as people are like focusing a lot on how to save energy. So we have this version which can give you the best energy with very little degradation in performance. And then of course very recently we have been working on this integrated network analysis monitoring. So those are the kind of all the different stacks we have. And this shows like a very simple timeline. As you can see, like the number of downloads have been steady. We are in a very rising curve of people downloading and using all the different versions. So this is a big architecture. I call it like a software family. So so if you in the middle, that's where you see our communication runtime corresponding to that bigger picture I indicated. So this is where we do all of our research, come up with the solutions. We support all the different networking technology, InfiniBand, IOR, Rocky, Omnipath. We also support all the modern architectures, starting from the basic Xeon to Open Power, MIC, KNL, also NVIDIA GPUs. And at the top, we have all these programming models. Not only just MPI, but pure PGAS, you can also do hybrid MPI PGAS. So that gives you, the end programmers, a complete flexibility of trying to see what kind of programming model is best for his or her application. So we do actually in a very in-depth manner. We have a very, we start with research because we are in academia, so that is our first thing. We just don't come up with some design and then just put it there. For the sake of it, we first experiment, we first publish, and then we publish them in conference and journals. But then after that, in 6 to 9 months, we take the best performing designs and then incorporate it to the code base. And in fact, we have a very rigorous QA procedure. If those of you are familiar, we have almost like these days 70 servers continuously running QA. Okay? Even though we are in a university environment, but we really give just like what you get from an industry, a very rigorous procedures, different kinds of unit testing, performance tuning, application-based evaluation on large-scale systems before we make the release. Even our alpha, beta versions also go through all these testing. So anybody is very welcome even to try out alpha, beta to see the features of the new capabilities. So these days we have now, with all the servers, we have capabilities like if we push a new design, around 36 to 40 hours, we can find out whether the code works or not. In all the tests it passes. We have very nice automated infrastructure to see what failed, and then we go back and then try to do all the kind of fixes, regression, just like any other industry they do to make this code ready. So this is the kind of like a bigger environment I briefly hinted here. This is the basic version, but then some advanced API features, the integration with INAM, PGAS and API PGAS, that is with MVAPICH2-X. The GPU is MVAPICH2-GDR, this is the MIC, this is for HPC cloud, this is for the energy aware. Then we also have not only the OMB, we also have an energy monitoring tool, so that you can actually see also how much energy is being consumed by your application, and then the InfiniBand network analysis and monitoring. So let me just touch base with some of these versions. What are the latest features and what are the kind of capabilities? So this one, if you are on our mailing list, you would have seen we made a release last week. This is the MVAPICH2 RC2. So we are coming very close. In another 1 or 2 weeks, we'll have a GA version out of it. So So the major thing we added here is the KNL, the support for KNL and Omnipath. So this has been tuned. If you have any large scale KNL cluster with Omnipath, you should be able to directly utilize this. This shows some sample numbers of the MVAPICH2 stack. This is like the latency. This is the large message latency of different adapters. So broadly we are here, like either you take Omnipath or ADR, we are around in the 1 microsecond latency. And then this is the large message latency, both like the InfiniBand UDR and then the Omnipath. They come very close. The ADR gives the little bit for the large messages the best latency. Then these are the kind of bandwidth. The left side is the unidirectional bandwidth, the right side is the bidirectional bandwidth. So here again we are able to go into 100 giga. These are like 12.5, 12.3 gigabytes per second. So if you multiply by 8, so this will be like 100 gigabits per second. And then these are the bidirectional bandwidth. So one of the things, these are the basic performance point to point, but as the systems have been scaling, you will see, like yesterday we heard about that also, and we will continue also today and tomorrow you will see some discussion. The job startup on this large scale, how quickly you start the job. That has been a big issue as the system size has been increasing. So we are continuously working on, there's a lot of solutions we have proposed, like not only improve the job startup performance, but also how much memory is required to all this, to make all these connections. Because that also we want to keep on minimizing. And then these are all the different kinds of solutions we have proposed over the years. So here you can see, like both for MPI and OpenSMIC, we can deliver you like a 10x, 30x improvement, even a 16 gigabyte memory saved for node with almost 1 million processes when you try to scale. Here it shows some detailed numbers, like let's say hello world. These were the earlier designs like the hello world and MPI init, and now we have reduced that, you can see, in a very significant manner using this non-blocking PMI exchange protocols. And in fact what we have done is we have patches available through Slurm, because many of these clusters use Slurm. So you take our design, and we also have patches for Slurm 15 and Slurm 16. And so you just have the patches and you will see this kind of performance on your cluster. So there will be more details in a student poster presentation. Saurabh sitting here, he will present. But there is also a new initiative with Livermore taking place, and Adam will go into much more details. That project is called Avalanche, and it's really looking at very extreme scale and how you can do this job startup and all with reduced to even few seconds kind of thing. So that is a bigger project we are working on. So, and that kind of support will be available in the near future with MVAPICH2. Yesterday we had a lot of discussion with GPU. We have been working very closely with NVIDIA for the last several years. Whatever all the latest features NVIDIA has, we have been working jointly with the R&D team to take that into account, not only for the basic point-to-point, intranode, CUDA IPC, tuned collectives, data types, all those things we have been incorporating. So we made this release 2 months back. And one of the things I'll show you this, yesterday there was a lot of discussion on this unified memory, managed memory. So we have actually very good, nice support for that. Yesterday these numbers were shown, kind of like working very closely with Davide, Sriram and all, working with the low level libraries. This is the kind of latency you get. That is the 2.18 microsecond you saw yesterday, like from a GPU on one node to the GPU on the other node, going over InfiniBand and then the switch, we get around like a 2.18 microsecond. And this is one of the things I really tell all my team members to get just. Sushil, will bring you in a little bit later. Hi Sushil. Yeah, give us another little bit, 15 minutes or so, we'll try to bring you in.
Sure, that's fine.
Okay, thank you. Yeah, thanks a lot. Yes, thanks. Okay. So this is the kind of performance we get, and there is no other MPI stack now which can deliver you this kind of performance. In fact, this version is being used on Thomas CSS system, so that's where you see good performance coming out. And here this is again some more details on the Cosmo, what we are working with the CSS folks. And it has been very nice working with these people. Many times what happens, just like a library designer, you just develop and then give it. But then these people come back saying, yeah, you are showing so much benefits in micro benchmarks, but I don't see it at the application. So, but this is a big challenge. We have been working very closely with them to see where that performance vaporizes, and then trying to see that, yeah, this need not be the best construct, or for example here, instead of like a default scheme, if you go through a callback or event-based thing, then only you can see this kind of an improvement. So continuously we are working very closely with them to push that envelope, like the Thomas indicated, the software infrastructure can give you more and more better benefits. So this is the unified memory. Yesterday it was discussed. This is the new feature from NVIDIA, where you can, irrespective of where you put the data, the user can, as soon as it touches, the data can automatically get moved. And we have provided the internal support together with the GPU Direct RDMA. So here you can see some 2D stencil performance improvement. Here it is like a bandwidth, you can get like a factor of 2.5 improvement. So then going into the MVAPICH2-X, so this is where I indicated, we started this part almost like 2011, the code came out in 2012. Now in the community you will be seeing there's a lot of discussion going on unified runtime, unified communication runtime, but this was the first we started in 2011. In fact, Santhan, who is sitting here, he was the architect of that design. We had the first paper, and we came up with this support for PGAS and then hybrid MPI PGAS. So that has been continuously making a lot of progress. And interestingly, you can do this using this stack. It gives you total freedom. You can write pure MPI program, MPI plus OpenMP, pure UPC, pure OpenSMED. In fact, we added QRA Fortran. We added recently UPC++. So we give this total flexibility to the user, and not only that, we deliver, since it is a unified communication runtime, whatever we do at the lower layer, we give the best benefit. Okay. So in the community, many times you will see people will say, my UPC program runs better than the MPI program. But then if you go inside, you will see those libraries are two different libraries. Or somebody else will say, my MPI program runs better than your UPC program. Okay, so they are doing actually apples to oranges comparison. But if you do this kind of stack, if you use, you really get apple to apple comparison. So that is our motivation to the community, so that people can try to see what works. So this is the latest release. Once again, here we provided support for KNL. All these models now actually work on KNL. You can also mix and match. So in this stack, there is like some of the advanced MPI features. Yesterday, Devendra talked about this on-demand paging. So that is a newer feature from Aeronox. And traditionally, the implement has been like it takes a pin down. That is the kind of registration logic. It consumes a lot of memory. But through these ODP designs, we are able to actually give you the same performance, but significantly reducing the pin down memory. And in fact, that allows for jobs to also run. If the job is requiring more memory, which cannot be run on a single node now, can actually run with this kind of ODP. And then there will be more details here on the student poster presentation. I think Nilze, who is sitting here, will be giving more details on that. So this is the UPC++ support. As many of you know, this has been coming from the Livermore lab, Professor Kathy Ellis group. They have been doing this UPC++. So now we have that support. Once again, you will see some more details in the student paper presentation. Now moving to the virtualization, of course there is two kinds of things are happening in the field. One is the very large scale data centers. All the supercomputer centers are deploying these large ones, but at the same time, for the smaller ones, many people are trying to think, how to do it in a virtualized manner, so that they don't have to manage, or some third party can manage. But the big problem has been the virtualization and HPC has not been going well together, because as soon as you go to virtualization, there is some overhead. And as you know, the HPC, high performance computing, nobody wants to lose the performance. Okay, so that has been the big challenge. So in that context, there have been some development, like newer technologies like SRIOV has come, which is the Mellanox has supported, and we have worked very closely with that SRIOV support. So just to illustrate the concept, here are some numbers. These are taken on the Chameleon cloud. This is the NSF initiative of across different institutions. OSU is a part of that to deploy virtualized environment for computer science research. Okay, not just for applications, but for computer science research. So traditionally, if you see, this is like the MVAPICH2 SRIOB default. So this line is the basic MVAPICH2 also will run. Okay, because in the virtualized environment will run, but the question is, does it deliver performance? And this is the native, the gray line, that is without virtualization, because that is the best you can get. Okay, and earlier this gap used to be like, as you can see here, like somewhere like 18%, 25% kind of things. But with our new design, we have been able to reduce it like 5%, 2%, 1%. Okay, so that means that one can actually make it, now the HPC cloud is, you can actually make it very realistic. And in fact, we have designed appliances based on this, and it's available in Chameleon. And now we are moving into the latest release, has actually container support, the Docker support, the same story. Through Docker also you can go and then try to see that the performance comes very close to the native. And then we are working on the newer directions like the Singularity, the shifter, those kind of stuff. Then on the energy side, as I indicated, like this is a project we started around 2 years back. So now we have an energy aware version, not only the API, but we also have a tool so that you can actually download. It doesn't require any root permission. You should be able to install on your system, and you run your application and then see how much energy is being consumed by your application together with the runtime. So this is, the design is based on the paper we presented the supercomputing in 2015. This was the best student paper finalist. So as you can see here, there are two, this is like there have been some solutions which are like a pessimistic MPI. This is the new design, and this design, this pessimistic MPI has been there for some time. It can save you energy, but it also affects the performance. Okay? So that is not good. I mean, if you save energy but you degrade performance, then nobody is ready to use that. Whereas this new design, you can see the red lines, we are able to give very good performance as well as the energy saving. And we also, here it shows like this across a lot of applications, we can have like a maximum degradation with, we can have like 41% saving at less than 5% degradation. And in fact, this has a very nice lever. You can say how much degradation you want to tolerate. Okay, so these numbers are 5%, but you can say no, I am ready to hold 15% degradation. In fact, that will give you much more energy saving. So you can do this kind of a dynamics between how much you want to tolerate the performance degradation and how much you want to save in terms of energy. So then this is the work I indicated, like the InfiniBand network analysis monitoring. Might be the next two slides will give more. So as a network system administrator, you can actually try to see what is happening in the network. This is like the Comet network at SJC. You can find out like how the links are becoming hot as the applications are running, which link is carrying what kind of traffic, what is the errors, all those kind of information you can find out. So this capability is there in many other tools. But the new thing what we added is job driven, because as a user, you want to see what happened on my job. Okay, and it has actually a database support. You can hold information for last 36 hours, 48 hours, depending on how much disk space you have. And then you can go back and say, okay, yesterday I ran this, what happened? Why my performance degraded? It could be that it interacted with some other job, or it could be your job itself didn't run properly with a good mapping. So all those kind of things you can drill down, and then it can give you all the different link utilization, job level view, node level view. So we'll have a demo session tomorrow where we'll be trying to show you all the capabilities here. Then I indicated OSU micro benchmark. So this project has been also going steadily. Every time we again add new stuff, new features, we always have a corresponding OMB version. Now let's see what are things ahead. Okay, so these are all the kind of things available, but we are very actively working on a lot of things. I just want to touch those base. Something along the application best practice, one build, there is a tag matching discussion took place yesterday, so we have been working on something, high performance fault recovery using re-init, performance re-engineering with MVAPICH2 and Tau, then high performance GPU based streaming application. This is a new project we have started. Control flow decoupling, yesterday we heard about the GDS, we have some solution. And this is a new field we have already entered, the deep learning. How do you take the GPU support and MVAPICH to optimize design for deep learning, energy awareness for MPI3 RMA model, extending OpenSMEM for accelerators, and then the HPC virtualization. So I'll just touch base a little bit and then we can discuss offline. So this is a new initiative we started. These days you see as there are a lot of different kinds of systems are out there, even though like we provide all the different user guide, all the parameter tuning, it's very hard for some end users to see what exactly works. So we have created something called a best practice. So in fact we have already collected a lot of these applications which are commonly running on different environments. So we try to, people have contributed. So if you go to this site, MVAPICH/best practices, you will exactly see what parameters are important for these applications. Okay? And we want to actually solicit additional contributions from all of you running applications on different fields to bring that information together and put it on the under one site, and with of course the credits to you, saying that okay, this is how you should run this application to get the best performance. And we hope that that will generate the user community, and then you don't have to waste a lot of time to see what parameters will work best for you. And this has been a big goal for us for some time, and Adam will remember this. He has been asking for, like currently if you see, we have the Mellanox Infiniment support, the QLogic PSM support, you have to build separately. So we are trying to unify the code base so that you can have actually with one build, you can build for both Gen 2 and PSM interfaces in one installation. And you can actually dynamically select the interfaces at runtime. So that will make the jobs of all the sys administrators very easy. We were almost there. We wanted to push it in this release, but I think we have slipped the schedule, so it will come out in the next few months in the 2.3 alpha kind of things, and then people can work on it. Yesterday there was a lot of discussion on tag matching, and we are very actively working on this. As you know, this tag matching leads to a lot of time complexity. But what people have been working on, so far all the schemes, whatever has been proposed, even that ISC best paper, these are static solutions. So what we have come up with a new dynamic and adaptive tag matching. So that means different nodes can actually select itself what tag matching it should use based on the communication pattern. Okay? And with that, you can actually see here, there are different schemes. Not only this, the green is the adaptive scheme. We give you best possible like a tag matching time. But see, the biggest advantage is the memory reduction. So you see, compared to this bean-based, rank-based, these are the green lines, almost negligible. We can reduce the data structures to do the tag matching. So in fact, this is the paper which will be presented in Cluster 2006. It has been selected as a best paper nominee and we'll be presenting that in the next month at Cluster. And this will be available in the future MVAPICH2 release. Then there is a lot of discussion taking place with respect to fault tolerance, as you know, in the MPI forum. So we are working with the group Reinit. Ignacio will give a lot of different details into here today. So the broad idea is that if this one, let's say process dies and we want to restart, so how you do currently the MPI stack can only do initialization only once. Okay? So this is a new paradigm we are entering so that you can do multiple initialization. And that provides a complete freedom. So in this case, like let's say this will restart, it will wait for others, everybody will reinitialize, and then they will continue. Okay? And then we have done a very nice design here. If you can see that the job restart compared to that, this reinit, it will take even like less than 4 seconds to recover from process failure within 1K nodes and 12,000 processes. Okay? So that's the kind of things we want to again provide the support in the upcoming MVAPICH2 release. More will be, Ignacio will be talking. Then this is the performance engineering I hinted earlier. MPI3 forum has started this, or the MPI3 standard introduced this called MPI-T variables. Earlier the MPI library was a black box. So you have a lot of runtime parameters and you need to run those things to see what is going on. So now these MPI-T variables has two kinds of capabilities. So it has a lot of performance variables. Through those you can find out what is going on, like what is the queue length, what algorithm is being used. All those information you can get and you can analyze those, and then you can control the library. So that is through the CVARs. Okay. So this is where we are working very closely with the TAO folks, and Samir again will give a presentation tomorrow. There are also poster session here, and we'll have also a demo session. So we have done a very nice integrated design as a first step, MVAPICH2 with TAO. So you, as an end user, you can just sit here and then do the performance engineering in a very automatic manner, saying what needs to be changed in the library, and so that the library tunes, automatically gets tuned for your application or your application's communication pattern. So then this is a new project which we have started here, I think with the Bracy who is sitting there. This is the Department of Defense project. The broad thing is that there is a lot of new kind of applications which are coming for streaming. So you think of like a surveillance or even a data coming from a single place, and then it wants to be broadcasted to a lot of GPUs to do very rapid processing. Okay? And this is where we are trying to combine two important features. One is of course the GPU direct RDMA from NVIDIA, then the Mellanox InfiniBand hardware multicast. Okay? So InfiniBand hardware multicast has been used in the host-based environment, but not in the GPU environment. So this is where we are trying to bring this together to a very high performance support. There is a, we just had a paper accepted yesterday, we heard about this. There is a, more details in the student paper presentation. King who is sitting there, he will go into more details. So this we will be enabling in the next MVAPICH2 so that for the streaming applications you should be able to also get very good performance here. Then yesterday there was a lot of discussion on this new GPU direct async that is the NVIDIA is proposing. That's the next step where you try to decouple the control flow and the data flow. So instead of host remaining in control of all the MPI calls, so here the question is how do you offload those into the GPUs so that as the kernels get done, automatically the communications will take place. So this is the that is the GDS lower level substrate. We have a MPI which is running already on top of that. So here it shows like let's say around 256 bytes. We can get around 25% improvement. At 1 kilobyte we can get 14% improvement kind of things. So you will be hearing about this very soon. There will be a public release, might be by the end of next month when the NVIDIA publicly releases the driver and Mellanox publicly releases the driver, then we will publicly release our MVAPICH stack so that people can actually try to use that. And for Thomas information, this is like we have been talking with Cosmo and all, this will have a big impact in how that Cosmo code can be rewritten to extract even higher performance. So we are already in discussion. So now going to the deep learning, yesterday we heard about the Nickel library from NVIDIA. So that is a library which is being proposed to accelerate this deep learning. But if you think the Nickel only works within a node, it has only some limited number of GPUs. Now all this deep learning, we'll have some talks later today. We will see that this deep learning are totally changing the way the MPI library needs to be designed. For example, they use like reduce, all reduce, broadcast with very large data. Earlier, like MPI library has always optimized for small data or medium data. So one has to rethink of these libraries, and that's what we have done. This is a work which is Nickel. We have extended it so that you use Nickel inside and also use the best algorithm outside. So now you can scale. You don't have to stick to only one node with limited number of GPUs. So here you can see like the collective you can get almost the factor 100x improvement. CNTK, that is a Microsoft framework for deep learning, and we have run on top of this. So here you can see like you can get almost 25% improvement. So in fact, this paper will be presented at Euro MPI next month, and it has been actually selected as the best paper runner-up to look at the MPI designs for the next phase. So once again, this is the plan to make it available through the MVAPICH2 release. And while we are working on the basic MVAPICH2, we are also working very closely with CAFE. That is another framework which is gaining a lot of prominence. So what we have done here very nicely is, again, you will see whatever CAFE people have been showing numbers with only 8 GPUs, 16 GPUs within the node. In this design, we have actually scaled it to see 128 GPUs. Okay, so now your CAFE can run, it can be scaled out to larger number of nodes with GPUs. We have a student poster presentation which will go into more details. Also, we'll have this OSU Cafe, which will be released soon, might be in a few weeks. You will see this will be coming out. So some of you might be familiar with, like, we have another project called Big Data. We have taken a lot of ideas from our MPI project to Big Data Hadoop Spark. So this is the third project we are starting. It's called High Performance Deep Learning. So that is where, like, we want to see how take the HPC knowledge or HPC technologies and the runtime middleware for deep learning. So that's the third project we'll be starting. So then I talked about, like, the RMA, the MPI3 energy aware kind of thing. So now earlier the design was only two-sided. Now we have even the RMA. Also you can have similar kind of energy saving. This will be available in the next release. And we heard about, like, different kinds of key gas. Earlier I indicated only the GPU support for the API. We have been working very also closely with in the OpenSMEM community. So this is where it shows, like, with OpenSMEM, you can actually bring all these the GPU driven solutions. So these are like some weak scaling GPU LVM, 2D stencil kind of things. You get very good improvement. And in this context, the OpenSMEM was not designed for GPUs. It was more for hosts, so we had to change some the paradigms from the OpenSMEM and then get this kind of benefits. So that will also be available in the future release. And finally, moving into the virtualization, earlier I indicated just the SRIOV and container, but people want to deploy it together with, like, a Slurm. So we have been working very closely with the features on the Slurm, so that you can run MPI applications with HPC clouds with Slurm in a very seamless manner while trying to preserve the performance kind of things. So these are the kind of things I just want to show, like, what is in the roadmap for the coming year kind of things. But this is our, like, long-term plans. As you know, like, I indicated, like, let's say if you take a Stampede, which is almost 500,000 core, so this is where we have reached. Our next goal is to go to 1 million core to deliver the best performance and scalability. And along those lines, so we want to touch with all these MPI plus task-based models, so that is becoming very important. Yesterday you heard about the SARP, so we'll be having some very tight design with SARP. There's some GID-based support is also coming. I think yesterday, I don't think Devinder mentioned. So this is to scale InfiniBand beyond the 64,000 limitation. So there are solutions from Mellanox, and we'll be trying to put the MVAPICH2 in that context so that you can go into more than 64,000 nodes. And then, of course, with night landing, with the MCDRAM, we have been very actively working on how to put different kinds of data placements and all within the MPI library to get the benefits of the MCDRAM and looking forward for the NVLink and CAPI. So all these are our like plans for exascale, and as we come up with solutions for these, we'll be able to push this into public releases. So with this, let me